Alright, let's take a look at an application of the derivative testing and curve sketching. So let's consider the function f of x is equal to 2x cubed minus 3x squared minus 72x plus 7. What is the maximum number of local extrema this function can have? Explain. What is the maximum number of points of inflection this function can have? Explain. Find and classify the critical points. Identify the intervals of increase and decrease, and state the intervals of concavity. Then sketch the function. Okay, so this is a pretty large question, right? Let's take a look at part A. What is the maximum number of local extrema this function can have? Well, if we're looking at a local extrema, we want to look at the first derivative, and we can understand that the first derivative here is basically the derivative of 2x cubed minus 3x squared minus 72x plus 7, which is basically 6x squared minus 6x minus 72. Okay, so this tells us that, right, we have a quadratic as our first derivative, and if you look at factoring this quadratic, right, you should see two roots, right? And you can actually tell that this is factorable, but if you wanted to prove that it had two roots, you can use the discriminant method, b squared minus 4ac, and if you did plug it in, right, this would actually be greater than 0. So there's two roots. So the two roots basically imply that there is two critical points. Okay, so that's why there's only going to be two extrema, right? And you can always remember it as, because the degree of this function is 3, you can always tend to expect a maximum of two turns, always one less turn than the degree of the function itself, right? And a turn is just basically a point of extrema. Okay, so it should at maximum have two extrema. Okay. So that's our explanation for that. Now part B here, what is the maximum number of points of inflection this function can have? Well, if you're looking at points of inflection, then you're going to be looking at the second derivative, right? And if I let the second derivative equal 0, then x is basically a point of inflection, right? So I need to find the second derivative to actually determine a point of inflection. I'm going to do a derivative of my first derivative. So I'm doing the derivative of 6x squared minus 6x minus 72, and you're going to get 12x minus 6. So that's your second derivative. And if you actually equate this to 0, you only see one solution, right? So if I let the second derivative function equal 0, you get 12x minus 6 is equal to 0, 12x is equal to 6, x is equal to a half. Okay, so you should have a point of inflection when x is equal to a half, right? Now we want to, so there should only be one point of inflection, right? And a point of inflection is when you have a chain in concavity. Now let's look at part C. Find and classify the critical points, identify the intervals of increase and decrease, state the intervals of concavity. Okay, so I'm going to change colors for this. So we stated, let's start with our critical points. We stated that our first derivative here is 6x squared minus 6x minus 72, and I factored this out as x squared minus x minus 12. I'm going to factor this, or simplify this a little bit more by factoring it, right? So if you factor this out, two numbers that add up to -1 that multiply -12, so let's do x squared minus 4x plus 3x minus 12 times 6. I'm going to factor these two and these two. You get x minus 4 plus 3x minus 4 times 6. And if you factor this by grouping, you can get 6 times x plus 3 times x minus 4. Okay? So this is basically your first derivative. If you want to find your critical points, I'm going to let the first derivative function equal 0. So you get 6 times x plus 3 times x minus 4 is equal to 0. So therefore x is equal to -3 and 4. Now these are our critical numbers of x. To find our critical points, you need to find its equivalent y value. So we can understand that our points are going to be -3 and f of -3, as well as 4 and f of 4, right? And in this case, f of -3 here, if I plug this into my function, you should get 2 times -3 cubed minus 3 times -3 squared minus 72 times -3 plus 7. So if I punch this in my calculator, I'll get 142. I'm going to do the same thing for f of 4. So that's going to give me -201. Okay, so my points here are -3 and 142. and 4 and negative 201. Okay, so those are my values, and those are my critical points. Now what we want to do here is we want to calculate or identify the intervals of increase and decrease. Well, if we're looking at intervals of increase and decrease, we can understand that if f prime of x is greater than 0, we have an interval of increase. If f prime of x is less than 0, we have an interval of decrease. Okay, so what you want to do here is we can generate a number line to identify this, and the intervals will be created when I plot the critical numbers of x, right? So my critical numbers here are basically going to be -3, so let's do -3 out here, right? And what I want to do here is let's make this this should not be inclusive, right? Because when it hits 0, we have extrema. Okay, so -3, let's say that. I'm just drawing this arbitrarily, there's no scale here. So we have -3 here. Let's say 4 is here. Okay, there's no scale. And they're not inclusive, right? So the intervals here are basically going to be, and this is -infinity, so -infinity and -3, right? There's going to be -3 and 4, and there's also going to be 4 and positive infinity. So this goes all the way to infinity. Okay? So let's test all of these out. Let's figure out the sign here. Right, so I'm going to pick a number between -infinity and -3. Let's do f prime of -4. Right, and if I have f prime of -4, if you plug it into your first derivative function, which basically will look like this. This is your first derivative function. You'll have -4 plus 3 is negative. Right, so you have 6 times negative. -4 minus 4 is -8. So that's a negative. And you have two positives, right? So this is a positive. So this is an interval of increase. Okay, so we have an interval of increase here. Okay, then what we're going to do is we're going to look at -3 and 4. Let's do f prime of 0. Okay, f prime of 0, this is going to give us a positive, right? 0 plus 3 is positive, 0 minus 4 is negative, so we're going to have negative here, so this is going to be decreasing, so this is an interval of decrease shown there. And between 4 and positive infinity, I'm going to do f prime of 5. If you do f prime of 5, this is positive and positive. So you have two positives. So it's increasing this way, so this is an interval of increase, right? And these are our intervals of increase and decrease. And according to our intervals, you can notice here that there's an interval of increase and interval of decrease. Well, if you draw a curve here, right, this is a concave down portion, so there's a critical point. There should be a local maximum at x is equal to -3. Okay, let's just make that a little bit more visible. X is equal to -3, and there should be a local minimum at x is equal to 4. Okay, so you can notice that the change in different types of patterns of intervals, whether they are interval of decrease, interval of increase, right? You can also be used to determine the concavity to an extent, as well as extrema, the type of extrema within your graph, right? So it's really useful, and you can also verify this using the second derivative test. Okay, so those are our first derivative test characteristics or criteria. Now let's take a look at the second derivative test. So I'm going to do the second derivative test out here. Let's use a different color. Okay, so let's take a look at our second derivative test, because we still need to figure out our point of inflection. So we said earlier that there is a point of inflection. There is a single point of inflection, and this occurred when x is equal to a half, right? So recall in part B, we wanted to find the point of inflection, right? And we have to use the point of inflection to figure out intervals of concavity. So when x is equal to a half, we know that a point of inflection occurs when x is 1/2 and y would be f of 1/2. Okay, so I'm going to do f of 1/2 here, and this is going to give me -29.5. Okay, so the point of inflection is 0.5 and -29.5. So that's our point of inflection. Specifically, I want to use the x value of the point of inflection to figure out my intervals. So I'm going to do that here. Okay, and if I'm doing that, what's going to happen here is, so we have 0.5 here. Let's put that here, right? This is 0.5. This is negative infinity. This is positive infinity. And let's figure out our intervals here. All right. So first, let's test out. This is the interval negative infinity and positive 0.5. All right. So let's do f double prime. And our second derivative function, I think we had it up here, actually was 12x minus 6. Right. So f double prime of x is equal to 12x minus 6, or if you factor this guy out, let's factor 12 out, you get x minus 0.5 if you want, or 1/2. And if I do f double prime of 0, right, you can see that you get 0 minus 0.5, it's going to be a negative, so this is going to be concave down, right? So f double prime would be f double prime of 0 is less than 0, right, and it's concave down, right? So we need to kind of remember that if f double prime of x is less than 0, it's concave down, and if f double prime of x is greater than 0, then it's concave up. Okay, so we also need to remember that. And then we need to test the second interval between 0.5 and positive infinity. Right, so if we do 0.5 and positive infinity, let's do f double prime of 1, and you should get a positive, so it should be concave up. And you can see that it's consistent because we should have a point of inflection or chain in concavity at 0.5. So this actually changes from concave down to concave up. Okay, so those are our intervals of concavity. And really the last step here is to sketch the function. Okay, so we can use all of this information to sketch the function. So I'm just going to make some space for this, and I'm going to write down all of our key characteristics. Okay, so here's all our information. From the first derivative test, we found that our critical points are -3 and 142. This identifies the local maximum, and 4 and -201, which identifies the local minimum. Our intervals of increase occur when x belongs to negative infinity and -3, union or 4 and positive infinity, and the interval of decrease occurs when x belongs to -3 and 4, right? In the second, when we did the second derivative test, our point of inflection was 0.5 and -29.5, and the graph was concave down when x belonged to negative infinity and 0.5, right? When x was greater than negative infinity but less than 0.5, and then concave up was when x was greater than 0.5 and less than positive infinity. Okay, so we can use this information, we can actually sketch the function out, and what would help is to find some intercepts, right? Although our x-intercepts would be very tedious here, right, you'd have to use remainder theorem. Let's first find our y-intercept. So if we find our y-intercept, you know what, I'm just going to use a different color for this, right? If we wanted to find our y-intercept, y-intercept occurs when x is equal to 0, so I'm going to let x equal 0, so you're doing f of 0, and that's going to give you 7, okay? So I'm just going to create a general plot, right? But if we did want a more refined sketch, you can use remainder theorem and find the x-intercepts. Okay, now this is going to be a little difficult because this won't be to scale, but we'll just kind of do our best with our sketch, right? So this is -1, -2, -3, right? This is 1, 2, 3, 4. Now for the y-axis, I'm just going to keep arbitrary scale, right? So don't worry about that so much. But in this case, for the x values, we have a maximum at -3 and 147. So let's put that right here. This is -3 and 140. Sorry, now 142, not 147. Right, so -3 and 142. And we also have a local minimum at 4 and -201. Okay, so 4 and -201, let's say it's like here. Yeah, this is 4 and -201. Right, we also have a y-intercept 0 and 7. So it should be right here. So let's say this is 0 and 7. Right, and we can understand that if this is going to be our maximum, this is going to be our minimum, right? We should essentially, this should be concave down, because we know it's concave down between negative infinity and 0.5. We also know that point of inflection occurs at 0.5 and -29.5. 5, right? So let's say it's like somewhere here. Okay, so if you're kind of sketching this out, right, you can kind of, right, just ballpark this for the time being. Okay, maybe we should use a different color for this. So what I want you guys to do is just plot the points, right? So this is 0.5 and negative 29.5. The scale of this graph is going to be a little bit much, right? I'm just going to recreate that really quickly. Okay. And, okay, so I just want you to plot your critical points, and we can understand that because this is a positive first degree function, right, it should start in quadrant 3 and end up in quadrant 1, right? So that's essentially what it should do. Okay, so this should be concave up. So between 0.5, this should be concave up, and there should be a minimum point, and there should be some kind of x-intercept here. Okay, so to make a more refined sketch, right, you would actually need to find some of these x-intercepts, right? But right now we just want to kind of understand the behavior of the function, right? So with using more tools, you can create a more refined sketch. But for the time being, I wanted you guys to understand the first and second derivative test in determining just general characteristics. But you can see here that there is an interval of increase between negative infinity and negative 3, right? So from here to here, you should have an interval of increase, which is consistent. Then between 4 and positive infinity, which you should see here, right? And there should be a decrease from negative 3 all the way to 4. So the derivative testing is very useful in determining the general shape of the